All right, so two things one thing I want to mention before we get started on this, and that is, I did post a formula sheet, and the formula sheet has the formulas from the different circle theorems that we've been working with this unit. So that should help you guys out when it comes to the test. And to be honest, even with some of the homework, if you guys, and with the review, so you guys it'll be easier to access and quicker to find. So today we're going to be working with segments. Okay, it's different segment lengths. Whereas in our last objective, we were working with angle measures and the circles and the secant lines and things that intersected there. So today, we're going to start off with this theorem. We have two chords that intersect inside a circle. Then the product of the lengths of one chord is equal to the product of the length of the other. Okay, and I think it's really cool how this works, but it will always work. So if we take the length CG, which is this length, and we multiply that times GD, which is that length, it will equal the product of EG times GF. Right? And it always works. Okay. As long as you got those two chords, right, they will always, the product will always equal each other of the two different chords. Okay. Let's see how this works. Well, I'll give you guys a second. I see some of you writing it down still. I think it's neat how this works. No matter how you draw the chords, you could have one chord that is the diameter length, and you could have another chord that's really small, and the products would still be the same. The reason being, if you take a long chord and then a real small chord, say this length, well, the product of the longer chord is going to be a really small number times a bigger number, whereas the smaller chord is going to be, those numbers are going to be bigger than that really small number in the long chord. So, right. Let's see this in action. So we got two here. The first one is just an example with chord or segment lengths that are known. So we can take, we got our two chords. Let's say we got one blue and one red chord. We take the product of the two segments in our red chord, 3 times 10. That should equal the product of our blue chord segments, 6 and 5. And they both end up equaling 30. Now, it's not always going to be just numbers given. It's going to be problems that are more like the one on the right, where you're going to have to solve for a missing length. In this case, we have a segment length that's equal to X. But I can do the exact same thing. Two chords. If I use my red chord segments, 6 times X. Equal the blue chord product, 4 times 9. 6x equals 36. Dividing both sides by 6. We get x equals 6. So we know that that segment, the missing segment length up here, is equal to 6. Right? Pretty straightforward. And when the segments are chords, when they're inside the circle, they're contained within the circle, pretty straightforward. It's two small segments from each chord product, I should say, those segments are going to equal each other. Okay, here's another one where we've got one chord has two segment lengths of 2x and x, so kind of two unknown lengths here. But we can set it up the same way. Again, I'm coloring one of these chords a different color just so it's easier to identify it. But if we take the red chord and we take the two segment lengths, 2x and x, we know that 2x times x will equal the blue segment, the blue chord segments. 6 times 9. Well, I know 6 times 9 is 54. 2x times x is going to be 2x squared. All right, well, if I want to solve for x, I need to divide both sides by 2. We get x squared equals 27. Okay. Now, unless the problem says round your answer to a decimal, we want to leave our answer in exact terms. So when I take the square root of both sides, 27 is not a perfect square. So if I simplify that, I know the biggest perfect square that goes into 27 is 9. And the square root of 9 is 3. So that is what x would equal. And if I wanted to figure out the other segment, it'd be 2 times 3 radical 3, which is 6 radical 3. Okay. Those will be exact answers. Sometimes you may be required, and we'll try to be specific. We want our answer in simplified radical form, or if we prefer it as a rounded decimal. And we'll try and be as specific as we can there on your assignments. If you're unsure, ask. Please ask. All right. Here we have some segment lengths, but now our intersection of those two lines or segments isn't in the circle, it's outside the circle. Okay. So we got, if two secants intersect outside the circle at a common exterior point, then the length of one secant segment from the common exterior point to the far side of the circle and its external part equals the product of the other secant segment and its external part. All right, that's a lot of words. It's a lot easier to remember this. Outside times whole equals outside times whole. Okay, so if we have two segments here, the outside part of that segment times the whole segment is going to equal the outside part of the segment times the whole segment. Okay. So you're still getting a product of two lengths, but it's not the two smaller lengths that you're multiplying together. You're multiplying the outside segment times the whole segment for each part that makes up the angle that intersects outside the circle. CE CH CD G. And what makes this a little bit more difficult is sometimes they don't give you, sometimes you have to figure out what that whole length is, or you have to figure out what the outside portion is. They may not give you, let's say, all three lengths, okay? Or segment CD, they may not give you what CG equals, what GD equals, and what CD equals. They may only give you two of those three. You got to figure out what the other part is. So here's an example where we've got this length is 9 on the outside, 11 on the inside, and then on the bottom part of this angle, we've got 10 on the outside and X on the inside. So we know that it's outside times whole. So if I take the outside 9 times the whole, and again, I could write it all out. I could do 9 plus 11. And then for the bottom part of this, we got the outside, which is 10 times the whole, which would be 10 plus X. And then some of this work could be done in your head. I mean, I could have done 9 plus 11 and made that 9 times 20. But I don't recommend you try and skip a bunch of steps on these. Right? I would have paper and pencil out so that you can write these down. 9 plus 11 is 20, so we got 9 times 20, and 9 times 20 is 180. This one I do need to distribute 10 to both parts. I can't, that's the only way I'm going to get rid of these parentheses. 10 times 10 is 100. 10 times X is 10X. I'm going to subtract 100 from both sides. 80 equals 10X. And if I divide both sides by 10, we get X equals 8. And I would say it doesn't look like it's drawn totally to scale, but not every picture will be drawn totally to scale. All right. So outside times whole equals outside times whole. Let's take a look at another example. Okay, here's one. It's very similar. Wow, I feel like my screen is flashing. Let's do the top part here. So we got 2 times 2 plus X equals 4 times, I'm going to go ahead and do the addition. 4 plus 6 is 10. 4 times 10 is 40. Let's go ahead and distribute the 2. 2 times 2 is 4. 2 times X is 2X. Subtract 4 from both sides. And divide both sides by 2. X equals 18. All right, these have been pretty straightforward because they've given us what I look as pretty straightforward lengths. This is essentially, and we've had these with a lot of them, where the tangent line parts are very similar to our secant line equations. And this one also is. If a secant and tangent intersect the outside of the circle, then the product of the secant segment and its external part equals the square of the tangent segment. It's essentially the same thing. It's still outside times whole. It's just that the outside and the whole are the same thing when you have a tangent line. Okay, this segment DC is both the outside and it's the whole segment length. That's why it ends up being DC's length squared. Good. So if you do have a tangent line, use the same idea, outside times whole. Right? You're just going to be having a squared number because it's the same length. quick example here. Gonna do the tangent part first. Outside times soul is just gonna be 20 squared. And then the second one is gonna be 8 times 8 plus x. 20 squared is 400. 8 times 8 is 64. 8 times x is 8x. If I subtract 64 from both sides, I get 336 equals 8x. I think when I divide it by 8, I think I get 42. So I know 320 divided by 8 is 40. And there's 16 more, so 2 more. 42. That's equals 42. Okay. How you guys feel about this so far? We got a couple more, but you guys doing okay? All right, so here's one where we're gonna get our missing length is the tangent segment. So that's gonna end up being x squared equals 12. And then we gotta do the whole. So we gotta do 12 plus 18, which is 30. I'm gonna leave that as x squared. 12 times 30 is 360, I believe. All right, so if I take the square root of both sides, unfortunately, 360 is not a perfect square. It's really close, 361 is, all right? So it's not a perfect square, but there are some, 360 is not terrible when it comes to reducing it. Let's do this. I think 36 is the biggest perfect square. That's 36 times 10. Taking the square root of 36, you get 6 radical 10. Okay. We got a couple more examples here. All right. You may occasionally get some problems with some factoring. Good, not terrible factoring, but a little bit here. So here we got some. Let's do the one with x on the left side. So we got outside is x times the whole. And this is where you gotta be careful. It's not just x times x plus 3. It's gonna be x plus x plus 3, because that's the whole segment length, equals 3 times 18. All right, 3 times 18 is 54. I distribute this though. Well, I'm making that a lot harder than I need to. Combine our like terms first. X plus x is 2x. Now we can distribute. 2x squared plus 3 equals 54. 3x equals 54. This is one where you guys did some factoring in algebra 1, right? Did you do factoring with numbers in front of x squared?
I remember.
Yeah. I'm going to subtract 54 from both sides. I get 2x squared plus 3x minus 54 equals 0. All right, so this is one where you can't really solve this. let's use our technology to solve this. We could use a graphing calculator. But I'm gonna use Desmos. Because we have access to that. And it should be a little bit easier to work with. So if I go over here and I open Desmos. And I type this equation in, which I just lost. Gives me two answers. -6 and 4.5. Which one makes sense? Well, does it make sense to have lengths of -6? No, it doesn't. Looks like our lengths here are going to be 4.5. I mean, we do x equaling -6 is a solution, but in this situation, it doesn't make sense. Okay, the 4.5 one does. So this length would be 4.5, and this length would be 7.5. There is a way to solve this, doing it as a factoring where we have.
Oh, so the bond is half of the one on top.
Where we get. Let's see.
Oh,
plus
so
6.
X. Wait, how do you figure out it?
We could factor that, and this trinomial could be split up into two binomials. You're gonna do a lot of this in algebra too.
So, wait, so X, is X,
It would split up to 2x minus 9
is
and
X
x plus
actually equal
6.
12? Do those sides have to be equal? Pretty much,
Which sides?
like the 15 and 3, and like,
This one and this one? No, they do not have to be equal.
but they're equal here.
15 plus 3 is 18. No, they're not equal, because 4.5 and 7.5,
I thought it's 7.5 now.
yeah, that equals 12. So they're not equal, but then they don't have to be equal.
Well, how do you figure out X?
That's what we just did. So you gotta do the
Outside times 4.
outside times whole, so x times x plus 3. We ended up getting an equation that had x squared term in an x term, which means we can't isolate x by itself. So the two ways to do it are to factor it, which we haven't practiced factoring at all, so I don't expect you guys to have to factor everything. So you could factor it, which would factor to this. Or we could take this and plug it into Desmos. And there's really, I plugged it in with it equaling 0. We could have plugged it in where it equaled y. And you still would get the same solutions. It's just your solutions would be part of this is a big parabola. All right, but your solutions are where it crosses the x-axis when it equals 0, which is still going to be at 4.5 and -6. So you got to look at your two solutions and figure out which one makes sense. Okay. All right, we're going to stop there. So you guys can get to work on your assignment.
So for the factoring, we haven't learned it yet, so is that why we can't do it? And that's